in this session we are going to look at image formation in projection lithography system. So far we understood image formation in the contact lithography. So now we are going to understand how image of the mask is formed on the wafer in a projection lithography system. So there is a little bit optics involved in this, but very basic optics, but I will try to explain whatever fundamental ideas of optics you need in order to understand the concepts here. So first let us look at the optical system that we have been so far exploring. So the projection system is similar to an optical camera. Right. So this is something that that we have been saying multiple times, where you have the illuminating optics and the projection optics, right. And all the patterns that we want to print on the wafer is captured in this mask. So there is a template that is already available, and we want to transfer this template onto the wafer. So the projection system, unlike contact litho and proximity litho, allows reduction of in feature size, right, between mask and wafer. So this is one of the very interesting properties of a projection lithography system. And typically the reduction factor could be 4x or 5x. What do we mean by this reduction factor? Let us take an example. So for instance, I want 100 nanometer line to be printed on the wafer, right, and the line width is, let us say, 100 nanometer. So at the mask level, if it is a contact lithography, I also need 100 nanometer, right, because it is 1 to 1, right. Whatever dimension you have in the mask is transferred to wafer. But in this case, because of the projection optics, we are able to reduce the feature size. So that means I do not need 100 nanometer at the mask level. At the mask level, I can have 400 nanometer. So 400 nanometer width is good enough at the mask level. So because I can reduce by 4x, I will get 100 nanometer by doing so. So there are a lot of advantages in doing this reduction. One primary advantage is the mask technology itself, right. So making this 100 nanometer would be very technology intensive, but making 400 may not be. Right. So we can make larger features and then reduce their size, right. So this is the shrinking that we can apply. If the die size, again, if this is on the wafer, so on the mask level the die size will be 4x, right. So all your circuits are going to look larger at the mask level, but when you project them onto the wafer, you are going to shrink it. So this is one of the main advantages in using a projection system. So before understanding the imaging, we should understand how the light propagates beyond the mask that we have, right. So we have a illumination from the left side. So you have a plane wave illumination to understand the basics, and then you have a mask, right. In this case, this mask has a little opening here that is going to create the spherical wavefront, and this is going to spread. The diffraction will start happening. This is a single slit, right. You must have seen this in your high school physics. And then you have another type of mask that has periodic openings. And now again we can go back to our Huygens principle that each opening will act as a independent source, and they will give out spherical wavefronts, and these spherical wavefronts also spread in different direction, right. So as they propagate, they also interfere with each other, right. This is the basic principle of diffraction from a single slit and multi-slit, right. and at a short distance, the diffraction is Fresnel. At longer distance, right, we call it as Fraunhofer diffraction limit, right. And if you look at the image at a longer distance, you are going to see interference pattern, right, and this interference pattern will have variation in intensity, and that will actually reflect the type of slit opening that we had at the mask level. So, this is how the image of this mask is captured, all right. So, let us look at a little bit more carefully how this diffraction happens by a coherent light source. So, light source we know. So, what do we mean by coherent, right? So, coherent is nothing but all the photons that are in that particular beam are uniphase, or the phase difference between the photons are 0, right. So, if I take a wave, this is a wave traversed by a photon, let us say, and then I have another wave, right. If these two waves at a given point of distance, when they are at same level, right, there is no phase difference, we call this as coherent photons. These two photons are coherent, and similarly you can draw multiple of this, right. And in the other hand, if I have a photon that is traversing this, and then I have another photon that is going in this direction, right, but there is a difference in the phase, right. So, it is not having your peak and valley at the same point, there is a displacement in this, right. So, this will create a phase difference, and this phase difference means the wave is incoherent. So, just to give you an example, a laser light source is a coherent light source, while an incandescent light is a incoherent light source, right, where you cannot focus it and so on. The reason why we were able to focus or propagate a laser without any divergence is because the phase difference is 0 and they will not diverge. Once you have phase difference, they will start diverging. So, that is about coherence. Let us look at how diffraction happens if it is a coherent light source, and we are just going to use a ray theory approach. So, you have a mask here, and this mask has this opening, and this opening is characterized by pitch, right, or periodicity, right. Both are interchangeable. We can either call it as pitch or the periodicity or duty cycle, so whatever suits you, but in this case we call it as pitch, and the opening is W, okay. And when the light is falling onto this mask, it is going to diffract, right, at a certain angle alpha, and the light from these two different slits are going to meet each other at a certain point, and of course at a certain angle here, whatever diffracted angle is here, right. So, one need to understand the interference between these two beams, right. So, these are all two isolated beams. Though their origin is same, they are coming from the same source. Now, as we just saw the Huygens principle, that they act as an individual light source, right. So, they are coming here and then they are trying to interfere here. So, what is the nature of this interference? So, if you zoom in, right, the location where you have the mask, you see here an additional path length, right, for this particular slit compared to the slit here, right. So, this additional path length dictates the phase difference, because the light in this arm will travel lesser distance compared to the beam here, right. If this if let us say this x is the distance, here x plus delta, right, is the distance that they travel. And as we saw, if there is a change in the path length, this path length is going to bring in some phase difference, right. So, as we saw here, so this is that delta x we had, right. So, this is going to bring us some path difference or phase difference between these two beams, and from the interference principle we know this phase difference is very important to create either constructive interference or destructive interference, right. So, your signal at the interference at the image plane here, in this case wafer, right, depends on the phase difference between these two. Okay. And the angle at which we come in depends on the order of diffraction, the wavelength and the pitch, right. So, this alpha. So, what does this alpha depend on? So, the alpha depend on your wavelength that you are using, pitch that you are using, and also the order of diffraction, right. So, n is just an integer. So, it can be 0, 1, 2, 3 and so on. We will see how these guys look like as we go along. All right. So, here the basic principle is, there will be a diffraction and there will be an angle difference, and this angle depends on your wavelength and your pitch, right. And now we are going to look at how this angle evolves, right. So, this is something that we already saw, sin alpha, right. The diffraction angle depends on lambda over p. And n is the integer, right. So, let us start putting in this integer into the equation here. When n is equal to 0, alpha is 0. So, diffraction angle is 0. So, there is no diffraction, there is a straight passage of this particular beam. So, when I put 1 and minus 1, you have lambda over p minus lambda over p. So, that is my plus 1 order and minus 1 order. These are all the diffraction orders, right. And then when I put 2, it becomes 2 lambda, minus 2 lambda, 3 lambda and so on. So, it keeps on continuing, all right. So, when I put a periodic structure and then illuminate it with a plane wave, I am going to get diffraction orders. So, this is a simple experiment that you could have done in your undergrad or in your high school, where you take a grating. So, this can be a metal grating or a line space grating in glass, and then when you shine a laser, right, you will see spots, right, and these spots are nothing but your diffraction order. That is what we are talking about. The one that goes undiffracted is 0th order, and one on the left side plus 1, minus 1, this is plus 2, minus 2. So, this is how a diffraction occurs, right. Any periodic structure illuminated with a coherent light source will create this diffraction orders, and you can clearly see that the orders, spacing and the pitch, they are all related, right. The angle, as you can see, changes, right, as you increase the orders, right, and it is related to pitch. Okay. When you change the pitch, this angle is also going to change for a given lambda, okay, in this case illuminating wavelength. And let us look at how this thing happens, right. So, I am presenting you with these two diffraction order image, right, the pattern here, and on the left side you can see the distance between 0th order and the first order, right, is alpha 1, and on the right side again alpha 1, but the alpha 1 on the right side is much larger compared to the alpha 1 on the left side, right. So, what is going on here, right. So, why the right side alpha 1 is larger compared to the alpha 1 on the left side. So, the only reason could be because this is all illuminated with same lambda, right, that is the assumption we have. So, we know that the diffraction order, right, depends, or the angle depends on your lambda, n is the integer, and your p. In this case only these two dictate, right, and this is a constant. And now the only difference that one could have between these two is change in the pitch. Okay. These two diffraction orders are coming from different pitch. Okay. So, that we understand now, because there is a change in alpha. But now the question is, one is larger, right, the left side, the right side one that you have here is larger, while the left side one here is less, right. So, how do we assess the pitch, right, whether pitch, I will call this pitch 1, and then this pitch 1, and this is pitch 2, right. So which one is larger, right. So the larger the pitch, right, the larger the pitch, your alpha is going to be smaller. So that means your distance between these slits, right, and this is P2, P1 is now larger than P2. So just to give you an example, P1 could be 100 nanometer, right, and your P2 could be 50 nanometer, right, the spacing. So if you have larger pitch, right, or slits that are widely spaced, right, the spacing between the slits are larger, then this diffraction order is going to be very densely spaced. And if the spacing is wider or narrower, right, then the diffraction orders are going to move away. Okay. So this is how we understand the effect of pitch on the diffraction order and the spacing, right, the spacing between the diffraction order, or you can also take that the angle between the diffraction orders also, right. So between the zeroth order and the other orders, how the angle is evolving. All right. So let's look at the image formation. Now we understand what happens after the mask, right. So in order to capture and make this image, you have to project the diffraction orders onto the wafer, right. So whatever diffracted light that we had, we have to capture it, and then we have to create whatever circuit we had on the mask, right. So the image formation is nothing but an intensity variation on the wafer, right. This is something we already know from our contact lithography, that the intensity variation is going to change the solubility of your photoresist. So the intensity variation depends on the intensity of each diffraction orders, right. So we have different diffraction orders that we saw. So how much orders we capture, it depends, will contribute towards this intensity variation. And to be very clear about this diffraction, I mean, for signal processing course, this might be very easy to understand. This is nothing but a Fourier pattern, right. It's just a Fourier transformation that we see, right. It's you take a pattern, and then when you illuminate it with a coherent light source, you create this diffraction orders. These diffraction orders are nothing but Fourier transformation of the pattern that we have here, right. So let's look at how that is, right. So this is how we create this diffraction orders, right. So there are different orders, and depends on the pitch, and then you can expand it as the Fourier series, right. This is nothing but a series expansion of the structure that we had. So this is the structure, and this is how it evolves, right. And let's look at how this diffraction pattern appears as a spectrum, right, as a diffraction order. So sin alpha depends on lambda over p, that is all clear, but now it is nothing but different orders that has some spatial frequency, right. So they are located at some frequency, you see here. So as you move away from the zeroth order, so this is zeroth order, right, this is +1, this is -1, right, and then this 2 is not there, and then you will have +3 and -3, right, and 5 and -5. So as you move outside from the zeroth order, you can see the distance between the orders change, right. This is something we all know from Fourier analysis, right, and this is also a very important property that will dictate the resolution, right. And if we want to reconstruct the image, right, what we do is we take all the orders, right. So in the series, all the different coefficients with various frequency, right, and then you add them. This is decomposition of a square pulse, isn't it? So you have this series expansion, and we have various sinusoidal decomposition of the square pulse, and this is nothing but our order, right? So these are all our orders. This is 0, 1, 2 and so on, right? So if you want to reconstruct this image, we have to capture, right, these orders and then add them, right? And this addition is nothing but the interference that we are talking about. So from the series, we know if we want to accurately reproduce this image, the square pulse, we need as many coefficients as possible, right? So if the series is infinite, the perfect reconstruction could be done by all the possible coefficients that we have. But in practice, it is impossible to do it, and that is the reason why we do this series, so that we can restrict our data, right, the data set. So for instance, I can reproduce the square pulse reasonably well, for instance, by just using 0, 0, 1, 2 and 3. So these are all the 3 coefficients that might be good enough for me to reasonably reconstruct. So we are going to use the same principle in image formation as well. So these diffraction orders that we see are nothing but all these Fourier terms, and I am going to put a lens to capture the diffracted light here, right? And this is what the job of projection lens. This projection lens is going to capture and then put them back into the wafer, right? So you take the image from the mask, right, and then by using projection litho, we are going to image it onto the wafer here, right, by using this lens system. And as I mentioned, you need to capture as many coefficient as possible, but there is a physical limitation of this lens, right? You cannot have very large lens, right? So the lens has a physical limitation, and that will be a some defined number here, right? So the resolution depends on the projection lens system. And let's look at how this projection lens system works. So we have something called numerical aperture of this projection lens, right? So this numerical aperture is defined by the refractive index of the space between my projection lens and the wafer. So this is the wafer, and what do I have between these two, right? It's similar to microscopy, right? If it is air, it is 1, and sometimes in recent days we use immersion lithography for advanced litho patterning. So there it's not anymore air, right? So we add some liquid into it, so it's not 1, it's going to be greater than 1, to be precise here. This can be greater than 1 if you put water or oil something, right? And here the Na is tunable, it's adjustable, right? In most of the system, this is a mechanical blanker, and we should be able to blank the beams between these, right? And now we can draw a relation and then understand this magnification a little bit clearly, because you have this incident angle coming from the mask after diffraction, and then we have this projection angle, right? So the tan theta I equals m times tan theta p. This m is nothing but the size of the die that you have on the mask to the reticle or the wafer that you have. So that is nothing but your size deviation, and the reduction factor is nothing but m, right? It's very easy to deduce this, right? So now we know where this reduction factor is coming from and how one can compare the effect of the Na, right, on the system, and also the incident angle and the projection angle. So now how do I negotiate the Na, right, on the image formation? So for instance, if my Na is low or my lens is small, I will be unable to capture all the diffraction orders, right? So I will be able to capture only few orders, right? But then if I have larger Na, or in other words a larger lens, I will be able to capture a majority of diffraction orders that we want. So this is basically adding more number of diffraction orders, in other words different or higher order Fourier terms, right? So when I increase the number of terms here, then my aerial image will be much better, or the reconstruction will be much image. The aerial image is nothing but reconstructed image on the wafer, or this intensity variation that we are talking about. All right. So, let us look at what is happening on the wafer. So, now we are slowly moving towards the wafer. So, initially we saw on the mask, and then we saw what is going to happen in this projection optics, and now we are on the surface of the wafer. So, now I have a 0th order, right, that is without any angle, and then now I have my first order, let us say this is +1, right. So, why the angle is different? The angle is different because now we are using this lens, right. We had this diffracted light going out, right, and then this is mask, right, and then now I have wafer. In the wafer I am capturing these orders and putting it back, right. This is the job of this projection lens, right. So, now that is the reason why you have this angle, and then now the angle is now changed because you are focusing it. So, this is the ray path, and what you see here are the instance or the wave with the same phase, right. So, if I have to draw it, the wave is propagating this way, right, from 0th order, and the other wave is coming from the other side, right. So, these are all the 2 orders that we have. And whatever lines that you see, this is what defines the equiphase. In this particular line, the phase is constant. And now, in order to create a constructive interference, you do not want any phase difference. That means the phase difference between the 2 beams should be 0, right. So, these are all the instances where you have same phase, right. There is no phase difference, and that is the reason why you have high intensity, right. And between this A1 and A2, the phase difference is non-zero, right, and that is the reason why you have destructive interference. At some point you have phase difference equal to pi, right, and let me name this as B, let us say, right. This is at B, right, and this is at A1 and A2, and this is between A1 and A2, right. So, the phase difference is non-zero. Because of this phase difference, right, you create this intensity pattern, right. This is how interference happens on the wafer and creates this intensity profile, and as we know, this is the primary requirement for us to eliminate the resist, right. And what is the resolution of this elimination, right? What happens if we change the orders, or if you add more number of orders, right? So, that is brought out with this simple calculation, right? So, if phi is the angle, right, at which my first order is coming, right, then you can write sin phi as lambda over delta A. So, delta A is the distance between the 2 constructive interference, right. And if you deduce this, you will get this, right. So, your delta A, the distance between these 2, depends on the pitch, the magnification that you have, and also your order, right. And now, if I tell you, okay, now I have only one order, but I can get more number of orders, right. So, here +1 is there, and let us see if we can bring +2 as well, right. So, what happens when I get +2? So, when I get +2, right, order as well, so my distance, right, between A1 and A2 can be reduced now, right. Initially it was delta A1, right, P over M, but now it is P over 2M, right, which is nothing but delta A1 by 2. So, that means I can create a structure, right, something like this with 3 orders coming in. So, as we already saw, the higher number of orders will allow us to image very small dimensions. So, now if delta A is this and this is the delta A, now if I use additional order, Okay. So this is how one can increase the resolution by adding or capturing more orders, right. And this is the resolution limit of the system. So you can see that the resolution of the projection system not just depend on the wavelength or whatever, there are multiple factors associated with this, right. So let's quickly look at how one can arrive at this resolution limit, right. So if I take only one order that is coming out, right, and then this is something we already saw earlier, what is the magnification that we see, and for small angles of diffraction that we get out of the mask, one can write the tan theta I as sin theta I, right, and then we can equate this with this, right, that we already know. So that will end up with an equation that relates your lambda with pitch to your illuminating optics Na and your magnification, and this is something very familiar, right. So minimum pitch that you can get over of course the magnification is nothing but lambda over Na, which is called our resolution limit. So this should ring a bell because lambda over Na is nothing but your diffraction limit, right. So now we have arrived at this relation completely different way, right, compared to traditional optics. So now the resolution depends on how many number of orders you capture, and we should also know that only one order will not create any image. Okay, one should be very careful. If you just use 0th order or only first order, that will not create an image. Image creation is always based on interference. So interference require at least 2 orders, right. So that's what is said at the end, at least one diffracted order is required to create an image. All right. So is this end of the whole resolution limit? Of course not. The problem with this is a theoretical limit, because in this case we only look at the optics, right. We looked at the magnification factor, we looked at the mask, right, and we looked at the Na. That's it. We did not consider anything else. So this is a theoretical limit. But is it better than what we see as a theoretical limit, right? So this only captures, right, the optics part. It doesn't capture other constituents in lithography that we really want to understand, right? That like photo resist, the baking, the development, all these things are out of the discussion in this resolution relation. So simply we cannot rely on this equation as the limit, right. So there is something else we need to add. So how do we add these process parameter, right? So we use a constant called K, right, in this case 2K or K, which is good enough, and this K is greater than or equal to 1, right. So you want this to be the value that will give you no, this should be less than or equal to sorry about that. So this should be the constant that dictates how good the process could be, right. And if I get a very good photoresist process, I control the baking, I control development, I should be able to get features that are lower than the diffraction limit that my optics dictates, right. So the resist process, if you use a very good resist process, you can get to 0.5 or so, right. So that means you can reduce your dimension and you can have better resolution, right. And one thing which I would leave it to you to think about is, what about the isolated lines, right. We so far we considered line space features, right. So now if I tell you that I only have one line here, so how is the diffraction going to look like, right? What is the resolution limit for such isolated lines, right? I will leave it to you to think about how these isolated lines are different from this dense line space pattern, because understanding dense line space patterns are important, because most of the fabrication, right, either it could be memory or it could be microprocessor based device, you will fabricate a lot of lines as gates and then metal lines as well, very closely spaced. So that is defining your resolution. Right. An isolated line is a special case. So just think about how this isolated line is going to look like in the diffracted pattern, right. So think about the pitch and everything. You should be able to understand how the diffraction pattern is going to look like and how the resolution is going to limit, right, or is there any limit at all, right, so to say. So this is how we create image, and in the next lecture we will look at how the image is converted into the photoresist. So now we were able to create a pattern, right, the aerial image or intensity pattern on the wafer. So now how this image or intensity pattern translates into the photoresist, and how one can transfer the pattern that we have on the mask onto the resist.